In this lecture, we're going to examine a situation in which we have more than two groups we wish to compare. And in this particular procedure, we're going to examine groups that are independent. So there's no overlap in the among the participants or the cases in the examination here. And in this scenario, we're going to examine a research study that examined the effect of post-exercise treatment on pain perception. And so our outcome variable, our dependent variable, is a measure of pain, and we're going to measure this along what's called a visual analog scale. So it's a scale in where individuals would rate their pain they experience after a bout of exercise along this particular 0 to 100 millimeter line, where a 0 would correspond to no pain and 100 would correspond to maximum pain. And the the independent variable in this case is treatment. And so after the exercise period, individuals are randomly assigned to three different groups, and within each of those groups, they carry out some form of treatment. And so the first group, right after the exercise, they would complete an ice bath procedure. The second group would receive a massage immediately post-exercise, and the third group would receive no treatment. And then following the treatments, the individuals would be evaluated for their post-exercise pain along this 100 millimeter scale. And the test that will be used to carry this out is what's called the Kruskal-Wallis H test. And this is the non-parametric equivalent to the one-factor or one-way analysis of variance. And note, this is not a repeated measures, so that the individuals assigned to each group only reside within those three groups. And we're going to evaluate the null hypothesis that there will be no differences in the ranks between the treatments. Once again, we're evaluating the individual's perception to pain along that 0 to 100 millimeter scale. And so, and that is contrasted with the alternative hypothesis that there will be a difference in the ranks between the different treatments. So what you see here are the three groups. The data have been collected. In the left-hand column, we have the raw data. So the first person assigned to group 1 rated along that scale a value of 40. The next person was 60, 10, 25, and 30. And you can see that for a number of values for group 2 and a number of values for group 3. Those data are then assigned ranks collectively, starting from the lowest value. So as we scan through the raw data, we see the lowest value here occurred in group 1. One person reported a value of 10, so they would have a rank of number 1. The highest rank was seen over here in group 3, where this person rated 85 along that scale, and so they have a rank of 15. Now the first step here, once we have the ranks assigned, you'll notice that, so before we go on, you'll notice that there are some tied ranks as well. So the tied ranks, if we have people that scored the exact same value, 25 and 25, then that is split down the middle, and we have a value of 2.5, a value between 2 and 3, and they both share that value. And then we also have another tied rank at 4.5, and so that's the average between 4 and 5. So we skip 3, we move to 4 and 5. We have two of the same scores here at 30 and 30, so each are assigned a rank of 4.5. So as we continue, the next step is to add vertically the ranks inside each of the three groups. So we see that the first group has a summed rank of 27, the second group has a summed rank of 29, and we see a quite a different value here for the summed ranks in group 3, a much higher value. So we can see that group 3, the individuals in group 3 collectively had ranks at the highest level as compared to the lower levels for groups 1 and 2. So that signals to us that there's possibly some form of difference among those three groups. And we always make note of our sample size, which is 5. And one more statistic that we need to calculate is the average ranking. So we just take 27 divided by 5 and we get 5.4, 5.8. And consistent with the summed rank of 64, we see the average rank for group 3 appears to be quite a bit different than that of group 1 and 2. And that's what we are going to evaluate as we move through this statistical procedure. But the first data that we need are the summed ranks. So to carry out the Kruskal-Wallis test, the first step is to calculate what's called the sum of squares. And this is an indication of the variability that exists between the groups. And this is going to be the key statistic here, or at least lead us to the key statistic. And so we use the prescribed equation where we have the sum of squares between, and we just simply add up the summed ranks for the first group divided by that sample size, which was 5, and we square the summed ranks. Once again, indicating that we're calculating the sum of squares. We repeat that for group 2, so we match up group 2 with and divided by 5, and then the summed ranks for group 3 divided by the sample size for group 3. And so substituting the data from the table, we have 27 squared divided by 5. We add that to the next sum of squares value, excuse me, or the summed ranks squared value, and we continue, and we have a sum of squares between that we will use moving forward to calculate our key test statistic, which is the H statistic. And as we saw up here, we have a prescribed equation that takes into consideration uppercase N. Note that we had lowercase n. Uppercase N is the total sample size collectively across all the groups. And we just simply take our total sample size, we feed that number, substitute that value into the equation, we multiply that by what we had just previously calculated for the sum of squares between, and we subtract this value, as you can see right here. So in substituting all the data, we end up with a test statistic of 8.66. So this is our test statistic based upon the data. The next step is to find the critical H value, and in this case we use the chi-square tables. And to do this, we need to know what our degrees of freedom is, and so this is the value that is dependent upon the study design. So we had 3 groups, or 3 different levels of this study, and so the degrees of freedom is just simply the k minus 1. And so we had 3 groups, subtract 1, and we have a degree of freedom of 2. And so what we want to do here is we want to locate our degrees of freedom along the column here, and we just calculated a value of 2, and unless stated otherwise, we're testing at the 0.05 type 1 error rate level, and the intersection here gives us a critical value of 5.991. So with these two numbers in hand, we then move on to step 4, and if the H statistic that was calculated from the data exceeds the critical value that's based upon study design, if that value is greater, then we determine it is statistically significant and conclude that the samples represent different populations of ranks, so that there's a clear distinction between those 3 groups. So we end up making a decision that since our test statistic of 8.66 exceeds our critical of 5.991, we reject the null hypothesis. Recall on slide number 46, our null hypothesis stated that there would be no differences in the ranks between the treatments. But since we now reject that null hypothesis, we conclude that the post-exercise treatments between the three groups were statistically different. And the next step is to find out which of those tests were actually statistically significant, statistically different from each other, and we will carry that out in the next video.